I'm glad to be here to share our research with you. My name is Li Zheng, and I come from Beijing University of Post and Telecommunication. Today, we'll talk about predictive uncertainty via active learning for regression-based QoT estimation in optical network. So what is the QoT estimation? Accurately estimating the quality of transmission of a lead pipe before its deployment is critical to optimize the planning of optical networks. Recently, machine learning is used to estimate QoT due to its fast and flexibility, but it is typically based on supervised learning. It learns a regressor from historical field data to estimate the QoT of unestablished lead pipes. We always take some lead pipe features, such as lead pipe's length, transmit power, and the number of links to form a vector. Feed into the regressor and the output is a QoT value, such as OSR, BER, GSR. In general, the accuracy of supervised learning is affected by the size and quality of dataset with ground truth labels. However, in real installation, collecting label data might incur additional costs. For example, establishing probe lead pipes require dedicated equipment and spectral resources. So we have to achieve accurate QoT estimation with the restricted sample size. When the number of samples is limited, active learning is always used to solve this problem. Given a small set of label data and abundant unlabeled data, active learning attempts to select more training-worthy unlabeled samples and query their labels for training. The purpose is to minimize the number of labeled samples for training a good model, and in this way, the labeling cost is minimized. Note that the key of active learning is a simple selection strategy. It means how to select more training-worthy unlabeled samples. Uncertainty sampling is a common simple selection strategy. It aims to select unlabeled sample, which the learner has the least confidence. That means they are more likely to be predicted incorrectly. Active learning with uncertainty sampling is applied for QoT classifier. The probabilities of misclassification is calculated from the output of classifier and denoted as the uncertainty of a sample to assign a training value for classification-based estimation. In optical network, regression is usually used to estimate specific values of QoT to obtain the specific information. But for regression, it is difficult to derive the probability of prediction failure from output and assess the uncertainty of a sample. Therefore, we investigate an active learning strategy for QoT regression. The results show that our strategy can achieve higher accuracy with fewer samples. First of all, we designed a simple selection strategy for regression. We introduced predictive uncertainty to design a simple selection strategy, which can evaluate which samples are more training-worthy. In other words, which samples are more difficult to estimate accurately. Predictive uncertainty is defined as the probability that predicted values will occur in the future. It characterizes how much the regressor knows about a sample, which represents the confidence in the regressor's prediction. For example, if a model trained on a dataset is applied to a completely different dataset, the model will have high predictive uncertainty. The large predictive uncertainty of a sample, the richer knowledge learned by the model and the more training worthy it is for QoT regression. At the beginning, we want to obtain the predicted uncertainty from the traditional QoT estimator. Given an unlabeled sample vector, the output of the traditional regressor is a point estimation. but the deterministic value could not capture the predicted uncertainty. So we train the traditional regression and construct a predicted uncertainty-aware model to output a predicted distribution. Given a simple vector, feed it into our predicted uncertainty-aware model, and the output we wish the output is a predictive distribution. It represents the probability of the possible predicted value for a sample. We assume that it obeys a Gaussian distribution, and we train the output layer of the model to contain true neurons, and they output true values corresponding to predicted mean and variance. And then we quantify the predicted uncertainty of each sample by calculating the entropy of the Gaussian distribution. Step 2. We choose an appropriate objective function. Based on both desired outputs, the negative, we choose the NLL as the objective function, which mirrors the discrepancy between subjective forecast and the long-term frequency. At step 3, we use ensemble to improve accuracy of our predicted uncertainty-aware model. To more accurately evaluate the predicted uncertainty, we use ensemble to form a uniformly weighted mixture model with several above basic models, whose outputs are mixed into a Gaussian distribution. Finally, based on above approach, we conduct a predicted uncertainty-aware active learning strategy. Firstly, the predicted uncertainty awareness model is trained with the labeled dataset, and then unlabeled samples are fed into our model, and the output is a set of Gaussian distribution. We quantify the predicted uncertainty and select the largest ones to deploy probe-like pies to obtain labels. Finally, we add them into the label dataset and update QoTS meter, and the above operations are repeated until it reaches certification accuracy. Finally, we validate our approach with simulation. We use an open source application, GNPY, to generate data and simulate the optical network. The configuration is shown in the table, and we collect 36 and 59 LightPies instances from Hall networks. Finally, we report the calibration curve for the single model and the ensemble model to mirror the discrepancy between predicted probability and observation frequencies. It can be observed that the max bias of the ensemble model is 0.06 and the one of the single model is 0.4. So it is indicated that compared with the single model, the curve of the ensemble model lies closer to the diagonal, represents optimal performance. It is indicated that the predicted distribution evaluated by the ensemble model is closer to the long-term frequency. It enabled a better awareness of the predicted uncertainty. Finally, we compared our method to a standard non-active offline supervised learning. Our method actively selects unlabeled samples for labeling, and as a baseline, the non-active learning randomly selects the same number of samples for labeling. All other conditions are identical. The prediction's accuracy was evaluated by mean square error, and note that due to the randomness of non-active learning, we obtain the statistic of its predicted accuracy by running it 50 times, and the results are shown as the box plot. The result is shown in the figure, and it can be observed that after adding 200 samples, our method achieves the average accuracy of non-active learning with 320 samples, with a sample saving of around 37.5%. And then, after adding 160 instances, our method almost coincides with the best of 50 randomly selected results. We analyze each point in the figure, and the result is shown in the table. It can be observed that with the same number of samples, the accuracy of our method is improved by 35.8% on average compared to mean of non-active learning. In conclusion, our method can actually select more training-worthy samples to expand dataset, which enable QT regression to achieve higher prediction accuracy with the restricted sample size. That's all. Thank you.
Thanks for the speakers in that talk. So any